All right, so one person sent me a question in advance, and this was asking about how to do Fischer projections for cyclic molecules. So the Fischer projections for cyclic molecules are actually easier than they are for linear molecules. The trade-off is that determining if something has a mirror plane to figure out if it's a mesocomplex is a lot harder. So what I'm going to build is what's called cis dimethyl 1,3-cis dimethyl cyclohexane. And to make this a little bit easier to see, I'm going to have a blue methyl group and I'm going to have a red methyl group. So I'm going to build my compound, and I've got, as drawn, I've got, oops, got them flipped around actually. Here's another, that's correct. I've got my red methyl group, and I've got my, sorry, rearranged this for my last meeting. I've got my blue methyl group, and I've got my red methyl group. Now, to draw the Fischer projection for a cyclic molecule, what you do is you just draw a rectangle, and this rectangle here is going to represent our ring. Now, it honestly does not matter if you use the left or the right side. I prefer to use the right side, just that's how I was taught. But again, if you use the other side, that would be effectively what you're doing is just kind of taking the ring and turning it to the side a little bit. If you want to put the ring on the other side, you're just rotating it the other way. Now, there are two ways to draw the Fischer projection. If you have a lot of CH2 groups, it's a little bit more efficient to make make both corners a CH2 group. If you find that too complicated, then the easier thing to do, for every carbon in this ring, put a horizontal slash. Now, to draw the Fischer projection, the way we originally had to do it for a linear molecule was we had to rotate it around so this way it ended up forming a coil. Well, it's already kind of in a coil. So what I'm going to do is I'm going to start with the blue carbon, and I'm going to turn it so this way I'm looking like I would with normal Fischer projection. So I've got the backbone carbons going backwards, and I've got the two groups coming forwards, and I'm going to look between them. So in this case, I've got a blue methyl group on the left and a hydrogen opposite. When I go to the next one, I've got two hydrogens. When I go to the next one, I've got my red methyl group on the left side, CH3, and I've got hydrogens, and the rest of these are CH2 groups. So for drawing the Fischer, again to recap, to draw the Fischer projection for a cyclic molecule, instead of drawing a straight line, you're going to draw a box. And on this box, the easiest thing to do is put a line for each carbon inside your ring. And then look at it like you would a normal Fischer projection. You can arbitrarily pick whatever carbon you want to be your starting carbon. I prefer to pick something with a functional group on it because it makes it a lot easier to see. And then you just start looking at your ring and working your way around. Now, if you flip the ring over, so the way I've got it here, I've got the methyl group. Sorry, I'm trying to flip it in my head. Methyl group on the right side. When you start rotating the Fischer projection, you're going to find that it's just basically this Fischer projection turned 180 degrees. So that was the only question I got today. What other questions are there out there? All right, so I'm not seeing any comments right now, so what I'm going to do, I'm going to pick up my banjo and just try a little bit of practicing. I am going to turn the volume off, but I do have the chat window up in case you have any questions. And yeah, for those of you who are just kind of following the background, when you see me put the banjo down, that means that somebody has asked a question. By the way, if you are that bored, I will turn the volume back on for you, so just let me know. Doesn't turn back on. So how you doing, Kaylee? Yeah, for Sako, like almost all your videos are coming from my website too. So she and I are working to update and improve the organic curriculum. So yeah, we're the two ones in charge of it right now. Big one we're looking to improve probably next year will be the labs. Yeah, you're going to notice a lot of similarity with our notes too. Yeah, she's improving the notes though, so I definitely agree with a lot of what she's done to it. And the big thing was getting her to get a second set of eyes on it. I'm glad you're doing well in the course though. Like I'm hoping like you've at least got a good foundation this time around. You're also getting the fun experience of another instructor who's never like this is the first time she's seeing the labs too. So yeah, we'll see what her candid responses are. Yep, this is her first semester teaching Organic Chemistry 1, and next year she's going to teach Orgo 2 for the first time as well, although not in the spring. But yeah, this is her first time teaching the course. I was glad to see she got promoted to it. We've been advocating for a long time that she move up for it. Because her background is actually pharmaceutical chemistry, I believe, so she actually has a really good background for talking about organic chemistry. Plus, she's done an excellent job in Orgo 1 or Chem 1 and Chem 2. So you can see from her teaching evaluations, like she's just a very effective teacher. But she's also sort of in the same position I was when I taught you, is that it was my first time teaching the course. So definitely kind of seeing that, like trying to gauge how fast to move and what to talk about. We definitely put that extra week for the first material to kind of like build the buffer in. Because in hindsight from your course, that was pretty intense to learn all that material that fast. So giving you that extra week just kind of builds a little bit of buffer in. I'll let her know you said so. She needs the encouragement right now. She is nervous because this is the first time she's taught the course. Because the speaking about instructors is the reason why instructors are so confident is they probably taught the course lots of times, so they know it inside and out. First time you've taught the course, you're really not 100% sure what you're doing, and you don't necessarily know when what you're saying is wrong. Yeah, so in place of doing live lectures, which is horribly ineffective for students, 4 days a week I have live streams where students are free to come in, ask whatever questions they have. I'll explain on the board, or if they have questions and they can't make it to live stream, I'll answer those at the start of the course. Now, this is open both to my Orgo 1 and Orgo 2 students, so I do try to preface if it's an Orgo 1 or Orgo 2 question, particularly if it's an Orgo 2, just not to freak out the Orgo 1 students. But yeah, you're also free to attend this if you want. You can ask questions. Like, this is an open office hour. We're still kind of early, so I'm guessing that's why not a lot of people are showing up, or they're not asking a lot of questions at this point. But yeah, this is just basically office hours. But as I learned over the summer, like, sometimes I have questions for the first 10 minutes and I spend the next 40 minutes, 50 minutes just kind of not doing anything. So my solution this semester was I'm actually like trying to practice the various instruments I have. So today's the banjo, yesterday it was the guitar, and the fiddle I'm going to kind of keep off the videos just because I've only been playing it for about 2 weeks now, and it still shows that I've only been playing it for 2 weeks. This I at least had the background with guitar, and honestly the banjo, it's easier to pick up if you already kind of know how to play the guitar. Bigger issue I found with the banjo is that it's played at such incredibly high speeds that it's very different than picking the guitar. But the chords are a lot easier. The goal is to get enough students with enough musical diversification or diversity that we can actually form like a folk jug bandish thing on the balcony. Because if you're going to be in southern Wake County, that close to Garner and Fuqua, you might as well have a jug band going just to kind of complete the aesthetic. I really feel like I connect with my Garner roots with the banjo. How's it go? Just 1 minute. Haven't been foraging, but have definitely found a lot. Mostly I haven't had a way to get it back out without anyone noticing. So last weekend I was walking Centennial, the lake around Centennial campus, since I figured, weren't going to be any students out there. And ended up coming across a lot of black trumpets that were growing on the far western side of the lake. And then also there's a lot of like chicken of the forest and hen of the woods that are like popping up right now thanks to all the rain. Also found a bunch of chanterelles, but they were baby ones, so I'm guessing people have already gone through and raided the big chanterelles. Hold on, someone decided to get herself stuck. I'll be right back. Oh, hush. This, by the way, is my cat, who is very upset that I'm not paying attention to her. That better. Yeah, great mushroom foraging weather right now. But again, no way to ship it back out without anyone knowing. Her main breed is what's called Nebelung, Nebelung. It's a weird breed that kind of like showed up in the 2000s, but she's not a purebred. You can see kind of the coloring where she's got some calico in her roots. But the main breed is a Nebelung. So they've got that long wispy hair. They've also got tufts of fur between their toes. And unique to their breed is actually they're highly OCD. I didn't know, because I didn't know this because it's actually my dad's cat. He gave me before I went to grad school. But they have like incredibly bad OCD. So like she has times that she wants to get up. She has times that she wants to be fed. They're also highly possessive. So when I come in here to do the live streams, there's a chair beside the computer because she wants to sit next to me. When I work by my computer, she wants to sit either beside me or behind me. When I'm making dinner, she wants to sit at the end of the kitchen. So like the breed is incredibly routine driven. And she does have the loyalty of a dog. I had a roommate that said like I would go out for walks in the evenings just to like get out, and she would sit by the front door and wait for me to get back. Yeah, she's a little glamour puss. I mean, takes great photos of her. Hard to believe she's 15 years old. She's also highly territorial, so there's a stray cat that I give her uneaten food to on the front porch, and like she still chases the cat off through the window. Like, I mean, he's a beta male. It's kind of entertaining to watch the other neighborhood cats just kind of push him around. Yeah, I'm thinking there's a lot of people that are out there hunting chanterelles right now. And I'm upset because the freezer went out at Wake Tech Southern Campus, so all the mushrooms I had in cold storage with all their baby roots, I even had some chanterelle roots that were in storage, are now basically lost to mold at this point. And I let them know 3 months ago the fridge had gone out, and to this day they still haven't fixed it. Yes, we're trying to get the formal reports out as fast as possible. So next week you're going to do a formal lab report on that lab. It is not the lab I'd rather you do a formal lab report on, but if we do end up closing down, it probably won't be next week, so at least you can get that first lab report done. Knock on wood, we haven't had any cases show up, and I'm assuming Wake Tech's going to be transparent, at least with the faculty in that regard. It's a straightforward lab. It's actually weirdly similar to a lab we used to do in Chemistry 1. Definitely one of those ones that's slated for improvement. But yeah, you're just separating 3 components and figuring out what the percent composition is. So curiosity, Kaylee, where have you been finding your baby chance? I'm optimistic we're not going to get shut down, just because Wake Tech is not engaging in nearly as much of the risky behavior that State and UNC did. Plus, we don't have dorms, which helps us quite a bit. Aw. I love the blue eyes on Siamese cats. Yeah, organic lab is not something that can be done online, and we're already being asked, like, what would you do as an alternative? Like, we don't know yet. Let's just cross that bridge when we get there. Lay down. Yeah, the study packets are definitely not mandatory. They're much more focused than the homework is. So the homework's going to be a little bit more scattershot in terms of like what it covers. But the lab packets, man, the practice packets are really just kind of meant that like that's the absolute minimum knowledge before you can start like approaching problems. Way to make the study session there, Kaylee. I figured you were just kind of like lurking in the background. Yeah, are you working for the guy that used to grow the mushrooms for the farmer's market? Because I had a research student that wanted to go there, but there was something weird about like the hours she would have to work. I'm glad to see lion's manes are starting to like come into vogue. They're just different. They're also really good at holding sauce. Okay. Yeah, North Carolina is weird because we have a lot of mushrooms that grow in symbiosis with pine trees. Usually pine trees are pretty, it's hard to find things that will grow with, but granted, I say weird because my foraging expertise comes from California, not North Carolina. So I find it weird when I find like boletes growing in symbiosis with pine trees because like redwoods, nothing will grow in symbiosis with a redwood, even though there's like ancient trees. So if you ever walk a redwood forest, you're never going to find mushrooms. Number 7. So number 7 is the cyclohexane with the alcohol and the methyl group. Use a darker pen than that. So this is the hardest one on that set just because it's just, well, I shouldn't say hardest. It's the most tedious. It is the most tedious problem. So it gives you cyclohexane and it says that you add a methyl group and you add an OH group to it. So off the bat, what are the combinations you have? So we can use a numbering system for this. We have 1 methyl, 1 alcohol. Is that actually visible? Barely, but it is there. So we can do the 1,1, and the next combination will be the 1,2. And then we can do 1,3 and 1,4. So just for ease, we'll just do the 1,2. Now, this is not chiral. It's achiral because if we look at this carbon, it sees the same thing going right as it does left. So if we were to look at the Fischer projection, we'd see it doesn't look any different. So this is the only version of this. This we have a couple of options. So each of these is a chiral center. And we have to make a decision. We're going to have both the R and the S configurations. So the way we're going to get that chirality is to have wedges and dashes. So we can have the methyl groups wedged, or we can have the methyl groups dashed. And the same thing with the alcohols. We can have them wedged, or we can have them dashed. Now the question is, do any of these contain a symmetry plane? Now the short answer is not one of them contains a symmetry plane. So if you go back to problem 6, that was the dimethyl. And with the dimethyl, we always ended up with a symmetry plane for what's called the cis conformation, so when they're both pointed out. For this though, because we lack a mirror plane, all 4 of these are unique stereoisomers. And you're going to repeat this process with the 1,3 and the 1,4. Excuse me. Yeah, the mushroom guy, good. That's a good experience. He actually, from what I understand, he has a really nice setup. He actually can control the CO2 and the humidity, so he can really control when his mushrooms bloom. Because my research student asked me that, I was like, well, can we get a CO2 tank? I was like, yeah, we're not that kind of college. We were trying to make them bloom in the back room, and that's really hard to do. We did get a few pins, but we definitely couldn't get any like full-blown mushrooms. So Elijah, does that answer your question about the number 7? Or at least how you would approach it? This is going to, you can ask Kaylee, this is going to be a foundation for when we go to alkanes. And definitely, if you're comfortable with the RS and kind of seeing the different stereoisomers and the different enantiomers, then the alkane material does get easier. I tell you and hope that she agrees. So enantiomers and stereoisomers. So isomers, big picture, isomers are things with the exact same chemical formula. When we talk about different types of isomers, not like molecules, but like different categories of isomers, we're referring to differences in how those chemical formulas are expressed. So for stereoisomers, they're all connected the same. So if we were to look at what atoms are bound to what atoms, they're all the same. If we look at the number of bonds, so the number of double bonds, single bonds, triple bonds are all the same. The difference with stereoisomers is that they are arranged spatially differently. So this is, a simple example of this is 1-butanol or 2-butanol. So every atom here is connected to the same thing. So this carbon's connected to 2 carbons, an oxygen and a hydrogen. This carbon's connected to 2 carbons and a hydrogen, and so forth. The difference is that with stereoisomers, they can't be spun around in space. They can't be twirled around in order to recreate each other. So it's like your left and your right hand. They look exactly the same. Your thumb's connected to your palm, your finger's connected to your palm, but there's no way to get my right hand to be the same as my left hand. When it comes to enantiomers, enantiomers have this rigid restriction that if we have, for every chiral center, we flip the symmetry. So if this was, well, this is our symmetry. If we flip it, it's going to be S symmetry. If we had 2 chiral centers, so we had fluorine and fluorine. This is RS, and this is SS. Let me draw the other combinations. So RS, RR, and SR. So enantiomers are where all the centers are flipped. So since this is RS, the opposite of is SR. So these two are enantiomers. This is RR, this is SS. These two are enantiomers. Diastereomers vary by 1, but not all of their symmetries. So enantiomers are the mirror image of a chiral molecule. Diastereomers are when parts of the chiral atoms are mirror images, but not all of them. So Kaylee is correct. If you had a mirror plane, you would have a meso complex. And for linear molecules, this is a lot easier to see in the Fischer projection because you can look up and down the molecule. So if we had OH, and OH. So we had this diol. And we looked up and down the molecule. We have CH3, CH3. And then we look at the sister compound, OH and OH. Come on, they run low on ink. So in this case, we've got an OH, an OH, an H, and an H. In this case, we have an OH, H, OH, and H. So for this compound, that's going to be RS. If we look at the Fischer projection, we don't see any mirror planes. But if we look at this one, even though it doesn't look like there's a mirror plane here, if we look in the Fischer projection, there's definitely a mirror plane. This part has a 1-to-1 on opposite sides of the mirror planes. So this would be a meso complex, whereas this would be chiral. Now, an easier way to think about meso complexes, they're their own enantiomers. So if you take the mirror image of this compound, you get this compound back. Meso compounds contain chiral centers, but the molecules themselves are not chiral. Now, this is the reason why I say it works better for a linear molecule is that if we take something like cyclohexane and we put 2 alcohols on it, it's kind of obvious looking at this loop that there's a mirror plane there, but if I draw the Fischer projection, it's not so obvious that there's a mirror plane because it's a matter of where I start my carbons in the loop. But yeah, enantiomers, big picture, is they're the mirror image of a chiral molecule. And the rigid definition is that all the chiral atoms have flipped symmetry. So if it's R, it's going to be flipped to S. If it's S, if it's flipped to R. Diastereomers, we've only changed a few of the chiral centers, but not all of them. So an atom with 1 chiral center only has an enantiomer. And an atom with 2 chiral centers has the potential for up to 4 stereoisomers. Now, the mesos come about. Basically, what happens is if you were to look at the symmetry of this one, so that's R, their symmetries are actually opposite. R and S are across that mirror plane because they are mirror images. And practically what happens is that chirality cancels out for meso complexes. So even though both these centers are chiral, the R and the S's negate each other. The big thing is for polarimetry. This R group is going to turn the light one way and the S group is going to turn it the other way. And since they're the exact same group, they're going to turn it the same amount and we don't get any optical activity. Yeah, you're very welcome. And the R in the S system is purely practical. Again, this is going back to the German roots of organic chemistry. The whole reason we pick atomic weight and atomic number is not because there is a fundamental reason to do that. It's German. It's very easy to look at an atom and know its atomic weights. You can't be bored. You have so much organic chemistry to do and biology and all the other courses that you're taking. But yeah, feel free to ask any more questions you got next week. Actually, Elijah, the real fun starts when we start talking about characterization. Um, but we're getting there. Hopefully this will click for you soon. Like, we're kind of like setting, it's hard to see what we're doing right now because we're setting a lot of framework down. But once we hit alkanes, hopefully this will all click together. Like, oh, that's why we did that. Oh, that's why we were discussing this. And you're now going to have this arsenal of tools at your disposal to approach alkanes and alkyl halides and alcohols and alkenes and alkynes and ethers. And you're going to be able to focus more on the reactions they do and less about how you characterize them and how you understand them. And I always believed that physics was not a hard field. I always feared it was a poorly taught field, and that physicists were intentionally obtuse in the way they explained things to justify like why they existed. I remember when I took electricity and magnetism in college, and it was a horrible, horrible course. Like, it wasn't well taught. They were trying to do a good job, but they weren't. And then I found out, I took a ham radio licensing exam, which there's a long story behind why I ended up getting my ham radio license. But I had a book that explained to, for being honest with ourselves, older individuals how electricity and magnetism work. And in 30 pages, it explained all of Physics 2 better than anything I took in college. Like, it even taught you how to work with the formulas, and it was much better explained. And that's when I began to realize that physicists, actually I realized this well into college, but it's the first time I really had direct evidence that physicists were making it way harder than it actually needed to be. I mean, that's why I kind of enjoy engineering physics, is that engineering physics is much more to the point. They're much more like, this is what this means. And particularly at State, that's where I got galvanized on the attitude that if somebody can't explain to you what the terms in their mathematical equation means, they don't understand the math. Like, they don't understand what they're doing. Math is a language, and if they can't tell you, oh, this formula represents this part represents this part represents this, they don't understand it. I mean, the worst quasi-physics course I ever took was a fluid mechanics course in grad school, and it was just math upon math upon math upon math. I cannot honestly tell you anything useful I learned in that course. In fact, we basically just kind of bluffed our way through the test knowing it was a graduate course and we weren't going to fail. Yeah, switching to online has been a shell shock for a lot of instructors. Because there's a lot you can get away with one-on-one in person, but it's another thing when you're having to teach someone asynchronously. Like, you're having to give them your information so they can understand it. It's like leaving directions for someone else. So if you've got a roommate and you want to leave directions for them, it's kind of that, and you're definitely seeing people that aren't very good at leaving directions, but they're a lot better at giving them in person. Now, on the upside, Wake Tech is forcing online certification on every instructor. So they are taking courses on how to teach online, but you're probably going to see that end result about December. Anything good on it? That's why I do all the speed on the school laptop that I'm all in for, because there's like nothing on this laptop interesting. My personal computer, which I do group meetings from, yeah, that definitely has some stuff on it. How do you find all the isomers or molecule, like when it's given a formula like C2H7N? So, yes, Pushing Electrons is an excellent book. I wish I could require it, but then again, I didn't use it in college, and it's also not a cheap book anymore. So, something like the molecular formula C2H7N. Well, the best way to do it, and honestly, even your book, even the Francis Carey book admits this, is to guess and test. So, let's consider a line, and let's consider a cyclic molecule. Now, carbon's going to have 4 bonds hanging off of it. Nitrogen's going to have 3 bonds hanging off of it. So anything we don't fill in with hydrogens, we're going to have to do ourselves. So we've got H7. So we need to do with 7 hydrogens. So we can put 1, 2, 3, 4, 5, 6, 7. So that seems to work, and since we don't have any double bonds, we can't do any like rearranging. If we had double bonds, we could definitely play with placement. For this one, 1, 2, 3, 4, 5, 6, 7. So there's your other combination. Now, I don't think it's going to work with this one, because typically when we do a cyclic compound, we lose 2 hydrogens to make that bond. So we got 1, 2, 3, 4, 5. So that doesn't work. So those are your only 2 possibilities. With isomers, it really is just guess and test. And I really do give credit to Francis and Carey saying that because even I tried to sit there with the back of the envelope, like, well, surely there's got to be a mathematical formula. Like, there isn't. So that's the other thing to keep in mind with this, is that you're probably not going to get more than 10 or 11 molecules. So start with a line, add a loop. If you have double bonds, make a first guess for where the double bond is, and then start moving double bonds along. If you have 2 double bonds, it gives you the option of 2 double bonds and a triple bond. Beyond that, it just gets unwieldy to figure out what's going on. So your book and tests typically stick to really simple examples where there's not a lot of play for what could be going on. Now that puts us as a disadvantaged instructors because it makes the question pool very small. But yeah, start with a line, change the order in which things are bound to each other, and then do a loop, change the order how things are bound to each other. Oh, actually, math will get to the point where you guess. First graduate math course I took, we talked about the Dirichlet problem. And the Dirichlet problem is this really esoteric math problem that I have no idea why anyone was trying to solve it. Yeah, you too. But the problem is that you have a 1-inch square that's heating an infinite space. So what's the solution? And I had no idea why anyone was trying to solve that problem, but they solved it by guessing. Like, they had a really good guess and it worked, but there is no backwards proof. And you find that with higher level mathematics courses, there's generally not a backwards proof. Meaning that you just couldn't sit back and go, oh, well, if you take this approach, you would arrive at this answer. You see a lot of guessing and testing and seeing what works out. Benzene was the same way. We didn't know the structure of benzene for a very long time until somebody had a questionably LSD-induced dream to figure it out. All right, Kaylee, got any other questions for me? It is actually nice to have students to talk to in these live streams. Otherwise, I'm just sitting here messing around on my instruments for a while. All right. So if there aren't any other questions, not with this compound. If you start putting in the hydrogens, you end up saturating all the bonds. So carbon's got 4, nitrogen's got the 3, carbon's got the 4. If you ended up like putting in all the hydrogens, so let's say you took 2 hydrogens off and you end up getting like, if you looked at it, you'd end up having basically either a carbon and or nitrogen not having enough hydrogens. So just in terms of isomers, there's only 2 options. Now I'm thinking about, I don't think there's even choices in terms of stereoisomers because these aren't chiral compounds. But yeah, start populating the hydrogens around, and if you find that like you don't have enough hydrogens to give every carbon all its bonds, that's when you'll start seeing the double and triple bonds. You don't have to make wedges or dashes on the isomers unless there is a stereo reason for doing it. So if you ended up with a chiral center, you could do that. But when you draw out the 2 structures, you see that there are no chiral centers on it, so there's no need for the wedges or the dashes. You could put them in there. They're not technically wrong, but because there aren't stereoisomers, it's not really important to put that wedge dash notation into it. Now, for stereoisomers, this isn't true. So if you end up getting a chiral center when you got done doing this, then yes, you would need to put the wedges and dashes, and for every chiral center you found on the molecule, you have the potential of an enantiomer to go with it. So if you have 2 chiral centers, there's 4 possible stereoisomers. If you've got 3 chiral centers, there's 8 possible stereocenters, or 3 stereocenters, 8 possible stereoisomers, assuming none of them are meso. But again, usually textbook problems and test problems don't get that hard, because you do quickly start walking into like really complicated territory, to the point that even, because for your course I tried to write a problem and I was like, oh, we'll go up to C5, and it just ended up, I was missing examples because there were just so many. So there's about a 10-second lag with my live stream. So when I speak, there's 10 seconds before it shows up on your end. This is just inherent to the OBS software as well as YouTube itself. So I can't really talk with you in real time unless I do it through Teams. And if I do it through Teams, the videos get really low resolution. So this was kind of 2 reasons I did the YouTube. One was that it gets me the ability to do the high resolution, or higher resolution than Teams. The second is that there are FERPA issues with students and Teams, so if you show your face in Teams, that can create problems in terms of your privacy and security. If I do YouTube, it's not a problem because you can never show your face. You're always online. So again, this is going to inherently create like a 10-second lag in anything I say to you. And then when you say it to me, there's a little bit of a lag that goes into that as well. Now I have had the lags go up to 20 seconds. That's my ISP. All right, so it is actually the end of the live stream. Kaylee, if you or anyone else is interested in watching these live streams, I do them Monday, Wednesday, 10 to 11 a.m., Thursday, noon to 1, and then Fridays, 2:30 to 3:30. This is just basically open office hours for me, so if this time works more conveniently for you, please go to Professor Sacco first. Like, she is your instructor. She can give you better answers in terms of what's expected. But this is not a territory thing. Like, if my students have questions, they're free to go to her. If you have questions, you're free to come to me. But yeah, other than that, thanks for y'all showing up, and I will see you all next week.